Welcome to Jibon Academy. This is similarity number 2. So we are going to be dealing with linear scale factors, area scale factors, and of course volume scale factors. Excel and Succeed is our reference material as usual. So without further ado, let us start. So by the end of this topic, you should be able to recall properties of similar figures from your Form 2. Should understand the relationship between linear scale factors and area scale factors. Should be able to calculate the areas of similar figures using the area scale factor. Should be able to apply similarity to solve problems involving areas. And of course, should be able to extend similarity concept to volumes of similar solids. So in Form 2, we saw the properties of similar figures in relation to angles and sides. Kunalizia angle, side, side angle, side. And in this chapter, we're going to use a similarity to calculate the areas of similar shapes and of course similar solids. So we're building on what you read in Form 2 into now calculating areas and volumes of shapes and different solids. So let us start with looking at this example where we have a square of dimensions 1 unit and 1 unit. So if I calculate the area of this square, it's going to be 1 times 1, which is 1 unit square. Which is a unit in every direction, in every dimension. We're going to have the second square, which is 2 units by 2 units. The new area for this, for the second square, is going to be 2 units multiplied by 2 units, which is 4 units square. Now, these two squares are similar. They are similar. Inner has been enlarged by a scale factor. From your Form 2A, we can get the linear scale factor, which is basically the ratio of the corresponding sides. So the second square has a side of 2 units, and the first square has a side of 1 unit. Then the linear scale factor is 2 over 1, which is what? Which is 2. So for you to get the second square, multiply the dimensions of this first square by 2. However, an interesting concept has also been observed under this circumstance. The new area is 4 units square. The original area, or the area of the first square, is 1 unit square. If we are to get the area scale factor, which is the how large has the area being scaled or enlarged, it's going to be 4 divided by 1, which is 4 units square. So to get the area of the second square, you need to multiply the area of the first square by 4. So the area scale factor is 4. It's 4. The linear scale factor is 2. If you look at these two figures, they are similar. We know that 4 is also 2 square. What does it mean? It means that the linear scale factor, if you square it, you're going to have the area scale factor. So you might be thinking, this is just a one-time scenario. Let us increase the second square by 1 unit both sides. Take the square 83 units by 3 units. So having that square, the new linear scale factor now is going to be 3 divided by 1, which is 3. So if you, to get the dimension of the new square, is supposed to multiply the original square, 1 by 1. You have to multiply it by the scale factor of 3. Now, the new area for this square is 3 by 3, which is 9 units square. The original square has an area of 1 unit square. So the area scale factor now is 9 divided by 1, which is 9. The linear scale factor is 3 divided by 1, which is 3. So this relationship still holds. So now we can generalize to say the area scale factor is equal to the linear scale factor squared. So here we have an example of triangles ABC and triangle DE. We are told that triangle ABC is similar to triangle DE. The area of triangle ABC is 6.25 meters squared, and the area of triangle ADE is 506.25 meters squared. Aribatsa length number sides for the triangles. For triangle ABC, we have been told that the length of AB is 5 meters. And for triangle ADE, we have been told that the length of DE is 22.5. We are going to find the length BD and BC. Now, first and foremost, we need to understand what have been given. Aribatsa areas. What do we know? From these areas, we calculate the area scale factor. However, the question is why the masculinity is a length of sides. So we have been given the corresponding or the area, the proportional sides of one triangle, and we're going to find the other in a similar triangle. So concept imene kufunika baba ya linear scale factor. However, we have been given the area scale factor. How do you get to linear scale factor? So we're going to use the relationship we have previously to get to that. So we know the ratio of the areas is going to give us the area scale factor. So we're going to divide 506.25 by 6.25. It's going to give us 81, which means the area ratio or the area ratio is 1 to 81. So to get the area of the bigger triangle, you're supposed to multiply the area of the smaller triangle by 81. That is what it's telling us. So we have calculated the area ratio. However, we're interested in finding my length of my sides. So as I said earlier, to go finding a linear scale factor to get those. So converting from area scale factor to linear scale factor, we know we have learned that the linear scale factor is the square root of the area scale factor. So the square root of 81 is 9, which makes the linear scale factor one or the ratio of the sides being 1 to 9. What does this mean? The first thing that we're going to find is the length BD. The length BD is denoted as X in the diagram. It lies on the portion AD of the triangle ADE. So you have been here to find the length here AD. How do you find the length AD? We have the scale factor and we have the length of AB. We know that the ratio of AB to the length of AD is 1 to 9. In other words, AB divided by AD is supposed to be equal to 1 over 9. AB length target 5 centimeters. AD is what we need to find. So we can make AD subject to the formula. Then we're going to multiply both sides by AD, and we're going to multiply both sides by 9. Having AD as a subject, AD is equal to 9 times 5, which is equal to 45. So the length of AD is 45. We are, however, interested in finding the length BD denoted as X. How are we going to find that? We're going to subtract the portion AB from AD. So it's 45 minus 5, giving us 40. So the length BD is 40. We also only want to find the length BC, given that its proportional side BE is 22.5. So again here, we're going to use the linear scale factor. We know that BC divided by DE is equal to 1 over 9. We're interested in finding BC, so we have to make a subject to the formula by multiplying by DE both sides. So BC is going to be equal to 1 over 9 times DE. DE is 22.5. So it's going to be 1 over 9 times 22.5, which is 2.5 meters. So the length of BC is 2.5 meters. So the answers are the length of BD is 40 meters, the length of BC is 2.5 meters, not centimeters. We are being told that the ratio of the corresponding sides of two similar triangles is 3/2. The area of the smaller triangle is 6 centimeters square. Find the area of the larger triangle. The first statement is when you use the linear scale factor for those two similar triangles is 3/2. So for us to get the area of the larger triangle, we need the area scale factor. We need to know how much to multiply the area of the smaller triangle to give us the area of the bigger triangle. So from the relationship the area scale factor is equal to the linear scale factor squared. So if you square 3/2, we're going to have 9/4. That is the area scale factor. Now, area scale factor, as you can see, 3/2 is 1.5. This value is greater than 1. So what does it mean? Here, greater than 1, it means the value here to multiply to the smaller triangle to get the bigger value. If the value is less than 9, less than 1, what it means is that this value to apply to the bigger triangle to get the smaller value. Where is this confusion coming in? It comes in because linear ratio, it's basically a ratio. You choose to divide how. You can divide the bigger side by the smaller side, or you can divide the smaller side by the bigger side. So 3/2, since it's greater than 1, it means that Alaba divide the bigger length by the smaller length. So it means 9/4 is the ratio of the bigger area divided by the smaller area. Now, to get the area of the larger triangle, we are supposed to multiply this by the area of the smaller triangle since we are enlarging it. So we're going to multiply the area of the small triangle, which is 6, by the area scale factor 9/4, giving us 13.5 centimeters square as the area of the larger triangle. So here we have exercises from 12.1, pages 150 to 251. We are told that the area, a rectangle whose area is 80 centimeters square, is enlarged with a linear scale factor 3. What is the area of the image? Linear scale factor and also the 3. What do we know? The area scale factor means we're going to square. So squaring is 9. So as you can see, 9, 3 is the linear scale factor. This value is greater than 1. It means we are to apply to smaller thing to get to the bigger. So 9 is the area scale factor which are going to have to the smaller area to get the area of the bigger. So the smaller area is 80 centimeters square. The bigger area is going to be 80 times 9 divided by 160, which times 9, which is 162 centimeters square. The ratio of two circles is 16:24. Find the ratio of the radii. B. Find the smaller circle diameter. The smaller circle diameter today. Find the larger diameter. So here we have been given the ratio of two circles 16:25, which is the area scale factor. To get the area scale factor, we're supposed to square. So squaring both sides, it's 4/5. Since the square root of 16 is 4, the square root of 25 is 5. So the area, the ratio of the radiuses is 4:5, or 4/5. So above it's now 4/5 is, I think it's 0.8, which is less than 1. It means this is a reducing scale factor. You are multiplying it to bigger value to get the value of the smaller one. So for the second part, which is B, I'm going to the smaller circle diameter is 28. Find the larger diameter. So in this case, to focus on this is less than 1. then it means we apply it to a smaller dimension to get the larger dimension. If we are moving from larger dimension to smaller dimension, we are supposed to do the opposite, the inverse operation of multiplication, which is division. So then to find the larger diameter, you are supposed to take the diameter of the smaller circle and divide it by that 0.8. Or you can use the proportions here. So the proportion you have to make you have to remember it's now the smaller over the larger, since it's less than 1. That's what I've been trying to say. So it's going to be 28 over d2 being equal to 4 over 5. If the linear scale factor was greater than 1, then would have been actually d2 over 28. It's less than 1, so it's going to be 28 over d2 being equal to 4 over 5. It makes up with the formula, it's going to be 35, which is the same value which can be found when 25 with 28 divided by 0.8. Now let us look at the volume scale factor. Auuza kuti the volume scale factor is the linear scale factor cube. Suppose tindi cuboid, a cube rather, 1 unit by 1 unit by 1 unit, and then we increase each dimension by a unit to get to the second cube, which is 2 units by 2 units by 2 units. The linear scale factor here is going to be 2 over 1, which is 2. However, the volume ratio is going to be 8 over 1, since the volume of this new cube is going to be 2 by 2 by 2, which is 2 cube, which is 8. Now, the relationship between the linear scale factor and the volume scale factor, we know that 8 is 2 cube. It is satisfying the formula that is presented there, that the volume scale factor is the linear scale factor raised to the power 3. Even if we increase the second cube into a third unit, which is 3 units by 3 units by 3 units, the linear scale factor is going to be 3 divided by 1, which is 3. The volume scale factor is going to be the volume of the new cube, which is 3 by 3 by 3, 27, divided by 1, which is 27. The relationship between 3 and 27 is that 27 is 3 to the power 3. So it is indeed satisfying the formula. Now we do the volume scale factor is the linear scale factor raised to the power 3. So here we have two similar cylinders, cylinder A, cylinder B. And also the linear scale factor there is 2. So radius of the cylinder A is 2 centimeters. The radius of cylinder B is 4 centimeters. Linear scale factor 2. The height of cylinder A is 4. The height of cylinder B is 8. So the volume of cylinder, you can calculate using the form of the cylinder 1 over 3 pi r squared h. It's going to be 16 pi cubic centimeters. And the volume of cylinder B is going to be 128 pi cubic centimeters. Now, if you find the volume ratio now, dividing the VB by VA, it's going to be 8. And we know that 8 is 2 cube. So it is still satisfying relationship we made about this previously. So here we have an example. We have been told that a solid metal cone has a base radius of 7 centimeters rather. It has a mass of 1.7 kilograms. We are required to find the mass of a similar cone. It's made of the same metal with a base radius of 10.5 centimeters. So what have we been given? We have been given the radius of the smaller cone and the radius of the larger cone. And have been given the mass of the smaller cone. and we are going to find the mass of a similar one, which is the larger one. Then, for what we have been given, we can calculate the linear scale factor, the ratio of the radii. So, taking the ratio of this larger to small, it's going to be 10.5 to 7, which is 3.2. Now, when calculating the volume scale factor, the volume scale factor is the linear scale factor raised to the power 3. So the linear scale factor is 3/2 or 3/2. So 3/2 raised to the power 3 is going to be 27/8. Now, ababa akuzotipeze mass. Why are we interested in finding the material? The key here is understanding that for solids of the same material, the mass ratio is equal to the volume ratio. If the material is the same, suppose we have the same density. So we're going to multiply, we're going to use the volume scale factor to get the mass, since we have been told that material of these solids is the same. So to find the mass of the larger one, we're going to multiply the mass of the smaller one by our scale factor, the volumetric scale factor in this case, which is 27/8. So the mass has been found to be 5.94 kilograms. So in summary, the linear scale factor is a scale factor in to malinga. So for two similar sides, or two sides that are proportional, the length of one side is the length of the proportional side multiplied by that linear scale factor. For the area of scale factor, even the scale factor apply between two proportional, between two areas of similar shapes. So they are in the area A, area B, also these areas are similar. The area ratio or the linear area scale factor of one, the area of one is equal to the area of the other one multiplied by the area scale factor. And the area scale factor is the linear scale factor square. And the volumetric scale factors are right to my volumes, and K, or it is equal to the linear scale factor cube. It is the same case for the mass, given that the materials of the two solids is the same, since they are going to have the same density. So you can try this just to check your understanding. The exercise 12.1, you need to attempt questions 1 to 8, and question exercise 12.2, attempt questions 1 to 6. So in summary, similar figures have equal corresponding angles and proportional sides. The area scale factor is equal to the linear scale factor squared. The volumetric scale factor is the linear scale factor cubed. For solids of the same material, the mass ratio is going to be the volume ratio. Always square for area, cube for volume. Keep units consistent when comparing measurements. Thank you very much. So keep practicing. Remember these formulas, where K is the scale factor, linear K, area is K square, volume is K raised to the power 3.